All right, started that video again and it did not go well, so here we doing it one more time here. All right, so we have another rigid body vibration example. This is problem 19.39 from the 10th edition, and this is a 8 kilogram uniform rod, and you can see that it's 1200 millimeters long, and it's connected to the spring right here that's got a spring rate of 800 newtons per meter, and it's attached to this disc, and it's pinned right here so the disc can't spin on its own. It goes together as an assembly. And this is a 12 kilogram disc, and the spring holds the thing at rest in this horizontal position. So it has an initial amount of deflection placed in there. Now they're going to say in the scenario where we move this point B down 25 millimeters and then release it, we want to find the period of the vibration and find the maximum velocity at B. So my approach here is different from what the example that I had previously. I'm not sure if I printed it out and posted it or not, but I didn't like the approach of the solution manual. I'm going to take the moment of inertia about B, get the moment of inertia about B, about A, excuse me. So we're going to, the rod is 1/12 the mass of the rod times the length of the rod squared plus the mass of the rod times the length of the rod divided by 2 squared plus the disc, 1/2 mass of the disc, which I called BC, radius BC squared, but then plus, it's going to be the mass of the disc, BC, and it's going to be moved by the length of the rod, so LAB squared. Put the numbers in here. 8 and 1.2 squared, and 8, and now 1.2 divided by 2 and squared, and the disc is 12 and 400 millimeters, or 0.4 meters, and then 12, but it's going to be moved 1.2 squared. So we end up with 22.08 kilogram meters squared. You take my word for it. In a lot of these problems, one of our strategies is to get rid of things we don't want to know to make it just a little more simplified, right? So that's a good strategy. So the thing to do to try to get rid of that is to remove some of the static forces, right? These are forces that are going to be, they don't really contribute much to the dynamics of them. So we want to try to get rid of them if we can. So we say, well, what happens in the static case so we go to static, there you go, or statics onto the thing. We're going to have the rod and the disc, and it's going to have this force right here. I'm not sure the right way to write this without it being redundant later on, but I'm going to say it's going to be, let me just remove it right here. Let me just remove it and call it K times the static deflection, right? We also have MAB, G, and then we also have from the disc right here, we have MBC, G. I forgot to put in the reactions. I forgot to call this an FBD, by the way. So this is RAY and RAX. So the sum of the moments are, about A is going to be equal to 0. And because so much is going clockwise in this problem, decide to break from tradition and make clockwise as being positive. Why not? So we'll say MAB times G times the LAB over 2, and now minus K static LAB over 2, and then plus MBCG times LAB is equal to 0. Right? You agree with that? Sure. We're going to use that later on. Now we move on into dynamics. But we got to spell dynamics right. Dynamics. And let's see, our FBD and IBD. I ran out of room before. I think I'm going to run out of room again. Let me see if I can get this fit into there. All right. So we're going to have boom. And I didn't bother using the straight edge this time. Gonna go freehand. Let's see what happens here. Oh, sorry about that. All right, so once again, we'll put our reactions in there. RAY, and here's RAX. They don't matter all that much. Now we're gonna have this force of the spring, FS. I'll write that below somewhere. And we're going to have our MABG. And we're also going to have our MBCG. And over here, because we took the mass moment inertia about A, we can just say that's going to be the mass moment inertia times acceleration, right? We don't have to do the virtual ones all the way through. So let me see. I'll write over to the static thing over to the side. We know that the static deflection is going to be K times, and of course this is drawn with a, at an angle right in here. So it is deflected by the static deflection plus the LAB over 2 theta right there, right? So this is the one that's, but because of the motion that's taking place, because of the dynamics, this is occurring and causing this, but it's also had the static thing inside there. So I might actually go ahead and distribute that out here. It would look easier. I'll do it over here again in a second. So that's like a little aside. So we'll take the sum of the moments about A, and we can say that right there, right? Sum of the moments about A. So let's write them out here. And once again, we're going to keep clockwise as positive. So I'm going to have MAB times G, LAB over 2. Minus, and now I'll go ahead and substitute that FS right in there, and I guess I'll go with the K. No, I'll put it right here. Minus K static plus K LAB over 2 theta, and that's the force. But now I have to be LAB over 2. And now that makes that a moment right there. And then we're continuing on with this. That's going to be clockwise, so we decided to make that positive. And we'll go MBC, G, L, AB. And that equals IA theta double dot, so that's also clockwise, right? So distributing this out, I guess I'll go ahead and write the thing out. You could see, then you're going to be able to see why we wanted to do this other thing before to get rid of it. I'm going to redistribute this out, and I'm going to group it together so you can see that it's all up there. M, A, B, G, L, A, B over 2 minus, I'm just going to use this part, minus K del static LAB over 2. And then plus MBCG LAB. Now I left out this part right here, so let me come back into there. Go minus K, and you'll notice that LAB over 2, but we're going to have 2 of them, so it's going to get squared. Theta equals IA theta double dot. But you'll notice up here, my big head wasn't in the way, is the same thing as this right here. So that equals 0. So now we have small terms. By the way, we had to make a small angle assumption right there. That should have been the sine of theta, but we made a small angles for small angles. Small angle assumption. So we could write out this differential equation, second order differential equation. You can see this negative, so it's going to come back over to this other side over here. And we're going to have K LAB over 2 squared over IA theta equals 0. And we know how to solve that. We know that we're going to have a natural frequency. It's going to be the square root of the stuff on the inside here. That K LAB over 2 squared over IA. And we have the values for all of this stuff. So K was 800 newtons per meter. LAB was 1.2 over 2 squared. And then we found our IA 22.08. And we're left with 3.612 radians per second. And part A of this was to find the period of vibration. So that's going to be the natural. We could have found the frequency. This is the circular frequency, but we could also find this by going 2 pi and divide it by that, right? So 2 pi divided by 3.6 ends up being 1.740 seconds. So that's part A, answer to part A. Part B asks for the maximum velocity of point B. So what we're going to need to do for that is write out, well, what is the answer to the differential equation? The answer is that we're going to have some magnitude times the sine of omega t, natural frequency, plus a phase angle, right? That is the solution. And they already told us that the thing gets pulled down 25 millimeters. That's what so if there's no damping, that's going to be the magnitude. It's going to keep oscillating back and forth between 25 millimeters. So, what is theta m? That's going to be the maximum motion of YB divided by the length of AB, or 0.025 divided by 1.2. Did I get that right? Yep. So that's 0.02083 radians. So we can put that back. We could put him in there. Let's take a second though before we go any further. All right. So that's what that. I don't need to write the thing out, because what I want to do is I want to find the velocity. So that kind of tells me I want to take I'm going to take the derivative of this, and so that's going to be theta dot is going to be theta m times omega n comes out of this, and now the cosine of omega nt plus a phase angle. And we want to know the maximum velocity, right? So the maximum angular velocity is going to occur when this right here equals 1, right? Because the cosine is just going to oscillate between 0 and 1, or maybe 0 and -1, right? Oh, no, 1 and -1, sorry. Back and forth the thing here. So the maximum of this occurs when theta m is times the natural frequency. So we can just plug in that number, 0.02083, and the natural frequency is 3.612. So we know we're going to get a maximum here of 0.07524 radians per second, right? Radians per second. I left off a per second here. And notably that we want to get the maximum velocity at B, so that's going to be the VB max is going to be equal to theta dot max times length AB. And so if we 0.07524 times 1.2, we end up with a VB max. I still didn't do a very good job of keeping this on the page. Ends up being 90.3 millimeters per second is what that turns out to be right there. And so hopefully this video took, because I'm not doing it again.